Hi, everybody. We are back for another segment here related to interval estimation. In the last segment, we had kind of discussed specifically what confidence intervals were, how to interpret that level of significance, and most importantly, how to interpret, what the confidence level actually means probabilistically. What we're going to do in this segment is discuss how to actually construct a confidence interval for a situation where we know some assumption related to the population standard deviation. So the assumptions here, first and foremost, the population standard deviation is known. We're going to assume the population is normally distributed. And again, even if it wasn't, we know we can exploit the central limit theorem in that provided we have a large enough sample, provided n is greater than or equal to 30 observations, we can assume that the sample means will be normally distributed even if the underlying population was not. So what we're going to do here is show how we can use this formula at the bottom to go ahead and construct a confidence interval, given that we've estimated some value of this parameter x bar, the sample mean. So x bar is not the tough thing to get here. We can do that, take the mean of the data. What is a little trickier is this term on the right, and this plus and minus means we're going to add that term to get the max value of our interval, and then we'll subtract that same term to get the min value of our interval. And that term is what we refer to specifically as the margin of error associated with our interval estimate. And this is the amount we're going to add and subtract from the point estimate to generate those upper and lower bounds on our confidence interval. Okay, if we wanted a smaller margin of error, right, a narrower confidence interval, there's a few things we could do to do that. You'll notice that square root n term is showing up here. And in fact, this entire term in parentheses should look familiar. That is the standard error of the estimate x bar from the sampling distribution, right? The standard deviation of that sampling distribution, where we had to make that adjustment for the square root n term here. Since that shows up in the denominator, you'll notice that if we increase the sample size, that would cause the margin of error to decrease. So we would have a more precise margin of error in some regard if we had a bigger sample. The other thing that we could do is we could lower the level of confidence. Okay, we could drop it from, say, 90 to 80, and that would cause that z value to actually get a little smaller, since we wouldn't be looking at as many standard deviations away from our mean, our sample mean underneath that sampling distribution. So let's go ahead and apply this formula to an example here. So this next example has to do with debit cards, and it says U.S. consumers are increasingly viewing debit cards as a convenient substitution for cash and checks. The average amount spent annually on a debit card is $7,790. Assume that this average was based on a sample of 100 customers and that the population standard deviation is $500. And what we want to be able to do here is to compute the margin of error, okay, which is going to be half of the distance between the min and the max. Okay, so just on one side is the margin of error. So let's go ahead and do that. And you'll notice we're given a few values here that are important. First off, we have a 99% confidence level, which we saw in the last video segment. If we look at those three commonly used confidence levels, corresponds to a z value here of 2.57. So I would plug that in. And then we're given two other pieces of important information. We have our sample mean, or so rather our population standard deviation, of 500, which is going to go here for sigma. And we're going to plug in our sample size of 100 in for n. So from this point, it's pretty much plug and chug, substitute those values in, and you should find a margin of error. And if you want to pause the video and calculate it yourself, you're more than welcome to at this point. But you should find that this comes out to 128.5. Okay, so if I wanted to construct the confidence interval, I would take that number and I would add it to that estimated mean, 7,790. That would give me the upper bound. And then if I took the sample mean of 7,790 and I subtracted 128.5 from it, that would correspond to the lower bound of the interval estimate. So here's another case study example here. A business manager is considering whether or not to continue using a particular vendor that has had some trouble with shipping. He knows that shipping times for this vendor have a normal distribution with a standard deviation of 3.5 days. So this might be gotten from past data, but he's assuming here that this characterizes the population standard deviation. And a random sample of 20 shipments from this vendor yields an average shipment time of 7.5 days. And what we want to be able to do is construct a 99% confidence interval for the vendor's mean shipping time mu. And here's what we are given. We're given that the sample mean from those 20 observations is 7.5. Okay, we're assuming that that population standard deviation is 3.5, and we have a sample of size 20. Okay, so at this point, what we need to do is, given that we're constructing a 99% confidence interval, we could go back to our standard normal table. We could divide that in half using the one-sided normal table. Or we can look at, in the previous video segment, the commonly used confidence interval values, and hopefully we would be able to find that the z-value threshold for the 99% level, again, corresponds to 2.57. Okay, so that's really the hardest part, is figuring out what is that z-value threshold. Otherwise, you're typically be given the other pieces of information here, right? Sample mean you would be able to get from your sample data. Sigma is some assumption about the population standard deviation. So given these values now, we can construct the margin of error just as we had done in the previous example. But now we're going to actually include X bar in our calculation. So if you simplify this term on the right here, you should see that that value, that margin of error, comes out to about 2, a little bit larger. And if I add that to the 7.5, then I'm going to get the upper bound of the confidence interval. And if I subtract 2.0011 from 7.5, then I get the lower bound from that confidence interval. So again, the interpretation here would be that the business manager is 99% confident that the average shipping time for this vendor is between 5.49 and 9.51 days. Now, again, we want to be careful in that we're not interpreting that as the true population mu has a 99% probability of falling in this interval 5.49 to 9.51. Rather, if we were to repeat this process, okay, we do this over and over and over again, let's say 100 times or 1,000 times or 1,000,000 times, and we kept doing this by sampling samples of size 20 and keep constructing these 99% confidence intervals, okay, out of 100 times, about 99% or 99 out of 100 would include that true population mean, and about 1%, 1 out of 100 would not. Okay, again, we cannot be certain whether or not the confidence interval contains mu or not. Okay, all we can really say here is the procedure itself leads to a situation where if we were to repeat the process over and over again, 99% of the time we would contain mu, and about 1% we would not. So again, he is 99% confident that the 7.5 daily average estimate, it falls approximately within 2 days of the actual value of mu. It is not correct to say here that the probability that mu lies between 5.49 and 9.51 is 99%. Okay, so let's go ahead and look at one more case study here related to subsidization of EPA mileage restrictions. And in this situation, we're going to consider a scenario where the federal government is thinking about giving a tax credit to an automaker that's selling a mid-size model equipped with an automatic transmission that has an EPA combined city and highway mileage of at least 31 miles per gallon. Okay, furthermore, to ensure that it does not overestimate a car's mileage, the EPA is going to obtain the model's mileage estimate by rounding down to the nearest mile per gallon, by using the lower bound, the lower limit of a 95% confidence interval for the model's mean mileage. Okay, that is, the model's mileage estimate is an estimate of the smallest that the model's mileage can be given our 95% confidence threshold at the lower bound. So here's the situation now. Let's suppose the automaker conducts a mileage test on a sample of 40 new midsize cars and obtains a sample mean of 31.308. Okay, and we're going to assume the population standard deviation here is 0.8 miles per gallon. Okay, you'll notice the 31.308 point estimate is above that 31 mile per gallon threshold required to receive that tax credit. Okay, but we also know there's sampling noise. If we've sampled 40 different cars, that mean is going to change, and it could be that the only reason we're above this threshold of 31 miles per gallon is because we had sampled the quote-unquote correct observations here. So what we want to do is determine a 95% confidence interval for the true mileage, right, for the population parameter mu. So again, here's what we know. We're given our sample mean, and we're assuming that population standard deviation is 0.8, and we have a sample size with 40 observations. And now, since we're using a 95% confidence interval, the z-value threshold that's leaving only 2.5% probability in either tail, this comes out to 1.96. Again, in a previous video segment, we saw that was one of the commonly used thresholds, the 95% threshold. And we're in a good position now where we, again, can plug this information into our confidence interval formula here, calculate that margin of error, add and subtract it to the sample mean. And the margin of error in this case comes out to be about 0.25, 0.248. So when we do that, we add that 0.248 to our sample mean and we subtract it from the sample mean. We find that the confidence interval ranges from 31.06 to 31.556. Now you'll notice the lower bound is still above the 31 mileage threshold. Okay, and it was the lower bound that they were going to round down to make sure that we were above. So if we were to do that, okay, note that our confidence interval here does actually qualify this particular automaker for that tax credit, right? The lower bound is above that 31 miles per gallon threshold set by the EPA. Okay, something to think about. And if you look through the slides, you'll see there's another example here. But if we had increased that interval to a 99% confidence level, think about whether or not your result would change, and if so, why. Okay, let's go through one more example here. We're going to think about constructing a 95% confidence interval for the average salary of a certified financial analyst charter holder. So the CFA designation is fast becoming a requirement for serious investment professionals. A recent sample of 36 charter holders shows a sample mean of $158,000. And the population standard deviation is known to be 35,000. So if you want to take a moment, pause the video and go ahead and compute the answer here, you might do that. Okay, and here's what we know. Okay, sample mean X bar is 158,000. Sample population standard deviation rather is 35,000. We have 36 observations in the sample, and again, for a 95% threshold here, our critical z-value threshold is at 1.96 standard deviations on either side of that sample mean of $158,000 salary. So once we plug that into our confidence interval formula here, okay, we can calculate the margin of error. And we now see that the confidence interval says we can be 95% confident that the true population mean falls within this range of $146,567 to $169,433. Okay, so best answer here is choice B. Okay, next question, important in terms of interpreting what we've just done. Which of the following statements is true regarding the 95% confidence interval? So if you want to pause, take a moment here, think about it. Okay, but again, the correct interpretation of this is that if we were to repeat the procedure of sampling and calculating confidence intervals from the same population over and over and over and over again, 95 out of 100 times on average, our interval is going to contain the true population mean mu. Okay, next question related to this one. If we calculate a specific confidence interval based on a sample, okay, then which of the following is true? Okay, well, A, note we cannot say that the true population parameter is in the interval with 95% probability. That is not the way to interpret the confidence interval. Okay, and again, C is not correct either. 95% of the time, the interval will be from 2.6 to 4.6. That's not true. If we resample different observations, we're going to get a completely different interval. Okay, so again, unfortunately, we're in this catch-22 framework where we do not know whether or not the true population parameter falls inside that confidence interval or not. Okay, so this brief video segment was how to go ahead and construct a confidence interval, assuming that we're dealing with normally distributed sample data and that we know what that population standard deviation is. We'll talk about how to adjust this process in a moment to deal with reality, where we maybe have to estimate that population standard deviation from our sample data itself. See you soon.